If I can't picture it, I can't understand it. Albert Einstein. Welcome students. In previous lectures in methods of work and energy, we have discussed work of a force, work energy theorem, its application in inertial and non-inertial frames, application of work energy theorem on system of particles. Today we'll discuss very important idea, that is idea of potential energy and conservative forces. In this lecture, we deal idea of potential energy in detail and conservative forces only qualitatively. Till in some later lecture, we discuss them quantitatively also and try to establish a relation between potential energy and associated conservative force. Now you can see on the screen in this figure, this person is pulling this string of the bow, and here is the arrow. When he leaves the string, the arrow gains kinetic energy. From where this kinetic energy comes? Actually, when he is pulling the string, he is doing some work, and that work is stored in elastic forces developed in the deformation of this bow. And this work which is stored as a recoverable energy, because when string is released, this energy is recovered as a kinetic energy of the arrow. One more thing, how to judge when this recoverable energy will be stored. That is, when a system is deformed, and to maintain the deformed state, if we have to apply the deforming force, then we can say yes, there is some energy stored. Before we explore further, let us discuss an experiment. Potential energy and conservative force. To develop a proper insight of these concepts, let us discuss an experiment. And that experiment is very simple. We simply take a spring block system, and how it is. Consider the setup shown, and this is setup. Here is a block. That block is placed on a horizontal floor that is frictionless, and the block is connected here with the spring. Other end of the spring is connected here on the fixed support. Now, if we pull the block and leave, the block will keep oscillating. Now, what we are doing here, force constant of the spring is K, mass of the block is M, and the horizontal floor is frictionless. We assume this to be frictionless, means we are assuming there is no loss of energy. Now what we do, we compress the block. Basically, we push the block, compressing the spring by some amount, say X, and we hold it there this way. Now it is compressed. Now to maintain the spring compressed, this person has to maintain its deforming force. What the force he has applied, that force has to be maintained. And this is an indication, yes, there is energy stored, because when this person will release his hand, this block will rush up here because of spring forces. Now the block is pushed gradually, compressing the spring by an amount X as shown in the figure here, that is description. And now we calculate something, work done by external agency in compressing spring, that we had done in the last lecture, and you can see that work done is equal to half kx square. Work by external agency is half kx square, and that is also potential energy stored in the spring. We have done it in last class. That is, after the block is released, its kinetic energy when it passes through the equilibrium position is K is equal to half mv square is equal to half k square, because from here we can use work energy theorem. What is work energy theorem? When the block is released, external forces on it are the spring force, gravity, and normal action. Under these external forces, it will move. Now when it passes to equilibrium position again here, till that point there is no work of gravity, because displacement is always perpendicular to gravity. There is no work of normal action, because displacement is perpendicular to normal action. Only the spring force is doing work. And how much spring force will do work? That is half k square, and that will be kinetic energy of the block. Now what we can say from here, how much work has been done by this external agency in pushing the block, that was stored in the spring as a recoverable energy. Why I am saying recoverable? Because when this block is released, this energy is recovered as a kinetic energy of the block. It seems that when configuration of the spring block system is changed from equilibrium to a state of spring compression X, the work done by the external agency is stored in the spring, because after the block is released, this is the stored energy which is recovered in form of kinetic energy of the block. That idea is very clear. Why I am saying this energy is stored as a recoverable form? Because when the block is released, the block gains kinetic energy when it comes here at equilibrium position equal to half k square. So we can say how much amount of work has been done in compressing the spring that was stored in the spring as a recoverable energy, and this energy is called potential energy. This recoverable stored energy in the spring due to its deformation is the potential energy of the spring. That is very important idea. And what potential is says? Why it is called potential? Because it has potential to do some things, to do some work, and it is recoverable because only when it has potential. The same result would have been obtained if the block were pulled, producing an elongation in the spring and then released. Of course, we would have obtained the same amount of result if the block were extended here by an amount x and then released. One more thing. In addition, the result will be independent of the path followed by the block. In fact, the kinetic energy of the block when it passes the equilibrium position depends on the amount of deformation of the spring and not on the path on which the deformation is produced. Actually, how will move the block? Of course, this person may move the block from this position to that position by on a zigzag path. It doesn't matter how, on what path this compression was produced. When the block is released, it will acquire the same kinetic energy. That is very important idea. And this idea will tell us something about conservative force. But before we discuss about conservative force, let us include friction here on the floor. Now we consider friction on the floor and see what happens. If we include friction, what changes it will do, let us discuss again here. Work done by the external agency in compressing or compression process. Actually, now when the spring is compressed, three forces acting on the block are gravity, normal action, spring force, friction, and the applied force. Of course, in the compression force process, gravity and normal action are not doing any work because they are normal to the displacement. But this external agency is doing work, spring force is doing work, and friction is doing work. Now you can see spring force is opposite to displacement, so it will do negative work. Similarly, friction will be opposite to displacement, it will do negative work. Again, the block was at rest here and the block is at rest here. So if you apply the work energy theorem, what we can say? Work done by all the forces between these two positions is equal to change in kinetic energy, and the change in kinetic energy is zero. So what we can say? Work done by external agency plus work done by spring force plus work done by friction is zero. So what we can say? Work done by external agency is equal to work done by spring force plus work done by friction. Now we can write here work done by external agency is half kx square plus mu mgx. This is work done by spring and that is work done by frictional forces. Of course, they were negative, but what equation we get here? W external minus half kx square minus mu mgx equal to 0. So what we get? W external is equal to half kx square plus mu mgx. Now you can see one thing. Of course, here again, this is the energy stored in the spring, but external agency is doing here more work. So what we can predict? This external agency is doing work in pushing the block from here to here. Some part of this work is stored in the spring and some part is continuously dissipated in the friction. I am saying continuously dissipated because friction is not capable of storing energy and dissipating it later. It dissipates energy as it receives energy. That's why I'm saying the word continuously dissipated. Potential energy stored in the spring is half kx square. So what we can say, it is not difficult to decide that if x is greater than or equal to 2 mu mg by k, for the block to return to the equilibrium position, actually what we can say, if deformation is greater than 2 mu mg by k, only when the block will return to the equilibrium position when released. And I am leaving to the verification of this idea to you. Now let us see the deformation produced here. X is more than 2 mu mg by k. If x is greater than or equal to 2 mu mg by k, the kinetic energy k of the block when it passes the equilibrium position, how we can say, Wi to F is equal to kf minus ki, that is work energy theorem. And how many forces are doing work on the block? The spring force and friction, because the block is now released, gravity and normal. Work done by gravity and normal is 0. So spring will do work and friction will do work. Of course, I am saying here the x is greater than 2 mu mg by k. So what do you get here? Wg plus Wn plus Ws, Wf, small f stands for friction, is equal to k final minus k initial. Now we substitute the values. Wg is 0, Wn is 0, Ws is half kx square, and this is minus mu mg x is equal to k minus 0. The final kinetic energy I am saying k. So what we can write about k? K is equal to half kx square minus mu mg into x. Now you can see, if the block returns to the equilibrium position with some kinetic energy, or say just returns here, then k will be 0 at this point. If the k will be 0, you can see x will be equal to 2 mu mg by k. Now if we suppose x is greater than this value, 2 mu mg by k, the block will return to the equilibrium position with some kinetic energy. And that kinetic energy we can find by this equation. It is clear that the total work done by the external agency during compression is not stored in the spring, as well as the total energy stored in the spring is not recovered as kinetic energy of the block after the block is released. Now what we can say, it is clear here. How much work has been done in the compression process, only this amount is stored and this amount is dissipated by friction. Similarly, when the block was released, this amount of energy was stored, but what is that? This total energy is not recovered as kinetic energy. Some portion, the work done by friction was dissipated in the surrounding as in the form of sound and heat. Here, the frictional forces make the difference. Now, why I am saying make the difference? Because in previous situation, when we have taken no friction on the floor, at that time what we have seen, how much amount of work was done by external agency, that much amount was stored in the spring. And when the block was released, how much amount was stored in the spring, that much amount was released as kinetic energy. But if there is friction during compression process, how much amount the work was done by the external agency, this part has been lost or dissipated by friction, only this part is stored. Now when the block is released, this part stored will not be recovered as kinetic energy because this part will be dissipated by friction. Actually, the work done by the friction force is not stored anywhere in the system, but it is continuously dissipated to the surroundings as heat and sound. Now it is very important. Actually, frictional force and spring force, you can see, they are two distinct type forces. The spring force has capability to store energy in it, but frictional force has not such a capability. What? As it receives energy, it dissipates it. It cannot store energy. So in this way, we have two kinds of forces. One which can store energy, mechanical, that is what we can say later potential energy, and other forces which cannot store energy. As they receive energy, they will dissipate this energy as losses, or there is another possibility. they will send this energy out of the system in some other form. Actually, we are not interested whether this kind of force, second kind of force like friction, will dissipate energy loss. What thing? It sends whatever energy it receives out of the system, whatever the form may be. It may be loss or it may be some other form. Thus, we encounter two types of forces in nature. What the two types? One type of force that stores mechanical energy in recoverable form as the spring force are known as conservative forces. Actually, those kind of forces which store energy in it in recoverable form, they are called conservative force. One of the example is spring force. And what is second kind of force? Like friction. The other type of forces that do not store mechanical energy but either dissipate it or expel it continuously out of the system as friction are known as non-conservative forces. Actually, this is the idea or concept behind conservative and non-conservative forces. Actually, of course, later we develop some mathematical theory about that to identify how which kind of force will be conservative and which kind of force will not be conservative. But that mathematical theory will be based on these concepts. So, to understand these concepts are very important. Now we proceed with making conclusions from these experiments. Conclusion of the experiments. The work done against the spring force was told as increase in potential energy during compression, and work done by the spring force during the extension after the block was released being decrease in the stored potential energy was utilized to supply losses in the friction and increasing the kinetic energy of the block. That is very important idea. Actually, here I am considering that the external agency is compressing the spring. Whether friction was present or not, work done against the spring force was equal to increase in potential energy in the spring, then that was the only stored energy. Actually, when there is no friction, it is very simple to understand it, because if there is no friction, the work force applied by the external agency is always equal to the spring force. So work done by external agency is equal to work done against the spring force, and that was stored in the spring. But when there is friction, the external agency has to apply now more force more than the spring force. By what amount? Equal to friction. So again, in this case, you can see, of course, external agency is doing more work. His work is being consumed against the spring force work and against the friction force. Again, you can see work done against the spring force is stored as the potential energy in the spring. But after the block was released, if the friction was present, then total stored energy was utilized in supplying losses in the friction and supplying kinetic energy to the block. And if there was no friction, the entire stored energy is utilized in increasing kinetic energy of friction. Now we can make important conclusion. It is also clear that whether friction is present or not, the work done against the spring force is equal to increase in potential energy, and work done by the spring force is equal to decrease in potential energy. Just see here, I'm saying this second one is a mathematical idea. First one, work done against a spring force during compression. Of course, you are compressing, it means you are doing work done against spring force. If there is friction present or not, as we have explained here, the work done against spring force was stored in the spring as its potential energy. But at the same time, I am explaining the same idea. At this time, work done against spring force means negative of work done by the spring force is equal to increase in potential energy. Now we can put the minus sign on that side. That is, positive of work done by spring force will be equal to decrease in potential energy. That is very simple mathematical idea. So that is what here, work done by spring force is equal to decrease in potential energy. Now what we can conclude, knowing the spring force which is conservative and internal force of the system, we can state that, what we can state? Now we are in a position to define potential energy of a two-body system in which internal conservative forces are acting. Potential energy of a two-body system. The work done by a conservative force is equal to decrease in potential energy of the system of the two bodies that are participating in the interaction responsible for the conservative force. That is very important idea. That is work done by conservative force is equal to decrease in potential energy of a system of two particles. What two particles? Those particles which are participating in the interaction that is responsible for the conservative force. So now what you can write here? du is equal to minus f internal conservative dot dr. This subscript int for internal and capital C for conservative. So what we have concluded here, that we are writing as a mathematical equation, that is negative of work done by internal conservative force is equal to increase in potential energy. Or we can say work done by internal conservative force will be minus du means decrease in potential energy. So whatever version you can write, but that is a fundamental definition or of potential energy. Potential energy defined as a change in the stored energy is property of the system. It is stored in the mechanism creating the associated conservative force. Again, this is very, very important idea. Why I am saying very, very important idea? Because in textbooks, before 11th class, of course, potential energy was introduced, but it was introduced as a potential energy of the body. You might be familiar with the idea, if a mass m is lifted a height h above the ground, it has potential energy mgh. Saying this way is not proper, but in lower class that idea was communicated. But now you can see where this energy was stored. If you are lifting a body of mass m to a height h, the potential energy mgh was not stored in the body which is being lifted. Actually, it was stored in the gravitational field between the body and the earth. Now, suppose you are lifting a body and leave it. If you are observing the earth and the body from space, equal forces are acting on the body as well as on the earth, but in opposite direction. So both should move, but being inertia of the earth is very, very large as compared to the body, acceleration of the earth because of that force and the movement of earth was negligible. Only what is apparent? Movement of that body which was lifted. So we can say potential energy of the body mgh. But actually in true sense, where this potential energy was stored? In the gravitational field. That's why I am saying the potential energy is not property of a body. It is property of the system. And system is at least two body. And where the potential energy is stored? It is stored in the force creating mechanism. Why I have taken here example of spring? Because spring is a force creating mechanism which is visible, or we can say that the potential energy was stored in the spring because of its deformation. But there may be forces like conservative forces which may act through field. So here force creating mechanism which is field will not be visible, but again potential energy will be stored in that field. So what is the idea here? The potential energy, which is a property of a system, it is stored in the mechanism creating the associated conservative force. So all these ideas are very important. Now we can say fundamentally potential is defined as a change, and for a two-body system, the two bodies or two particles which are interacting through conservative force. Now we can extend this idea for a system of many particles. Potential energy of a system of many particles. How we can extend? That is very logical, because in a system of many particles, we identify those particles which are interacting with each other through conservative forces. Now if we change their positions, what you can say? We are changing configuration of system. In that way, the potential energy change will be associated with all those pairs of particles which are interacting through conservative forces. Now I am writing this idea here. Change in potential energy of a system of particles between its two configurations is the sum of changes in the potential energies of all possible pairs of particles interacting through conservative forces. That is very important. Of course, we may have n particles. Out of those particles, some of the particles may be interacting with each other through conservative forces, and some of the particles may be interacting through each other with the non-conservative forces. Or maybe between two particles, both the forces are simultaneously acting conservative and non-conservative. So if we change configuration of system, what is potential energy? That will be associated to all such pairs of particles which are interacting through each other by conservative forces. Now, one more thing, what we can say from here. Now, if you want to find change in potential of your system, what we do? We calculate change in every pair of particles which are interacting through conservative force and add all those changes. That is what we can say potential energy of a system of many particles. Again, here is very important thing, configuration. Actually, in physics, whatever terminology we are using, we must have its very precise definition. So, how we can define that is configuration? Again, I've signed definition, means definition is a mathematical statement. So, how we can define mathematically configuration? Let us see. Configuration. It may be defined as the set of position coordinates of all the particles of a system at an instant. Now, the idea is very clear. If position coordinate of any of the particle will change, we'll say configuration of system is changing. And if there are internal conservative forces, potential energy will change. So that was the idea behind potential energy of a two particle system and potential energy of a many particle system. I'm summarizing things. For potential energy of a two particle system, fundamentally is defined as a change, that is work done by conservative forces between the particles will be equal to decrease in potential energy, or you can say negative of work done of that conservative force will be equal to increase in potential energy, and that potential energy will be stored in the conservative force creating mechanism, not in either of the bodies. And here the same idea is extended to many particle system. Reference configuration, again here very important thing, that is potential is defined as change, but still we can say potential energy absolute value. Of course, there is no meaning, there is no sense of saying absolute value of potential energy, but of all possible configurations of a system, to one configuration we can or we may assign zero potential energy. If it is possible to assign zero potential energy to a configuration of a system, then for other configuration system, its potential energy we can say absolute potential energy, or we can say like absolute potential energy but not absolute potential energy. That is what in this case, if you are lifting a body from ground, when the body was at ground, we say its potential is zero, means potential system is zero. Now if it is lifted to height h, work done by extension is mgh, will be stored in the body or system as its potential energy. So we say now potential has become mg because initial was zero. So if in some situation to a particular configuration we can assign zero value, then to other configuration we can say some absolute. Their values, of course they are changed, but we can treat them like absolute values. The potential energy is defined as a change in its value between two configurations of a system. Yet in some situation it is possible to assign its value to be zero in a particular configuration. In such situations, the configuration assigned zero value to potential energy is chosen as a reference. That is what idea. For example, the relaxed state of a spring is chosen as a reference to define potential energy stored in the spring. Actually, when we are defining potential energy, most simple idea, when it has relaxed state, we say there is no stored energy in the spring. So that is what this configuration of spring is taken as reference. Now, for any deformation, whether it is a compression or elongation, say amount x, how much energy is stored in the spring? Half kx square. Actually, it is change from relaxed state. To a relaxed state, we assign 0, but we can assign some other value, say u naught. When spring was relaxed, say its potential is u naught. Say I am assigning not 0, some value u naught. So when the spring will be deformed by amount x, it stored it, how much change in potential energy? U naught plus half kx square. But if you say stored means, that is change from first configuration to other configuration. So defining a 0 reference or to defining a 0 potential energy to a particular configuration will simplify our calculation. But in some situation, it will not be possible to define a configuration to have 0 value. In that situation, we proceed with the fundamental definition of potential energy as a change. Gravitational potential energy for a uniform gravity or uniform gravitational force. Now, whatever idea we have developed, we try to develop some expression for different in different cases for potential energy. So first example, what I am taking here, gravitational potential energy for a uniform gravitational force. Now that is again very important. We generally say when gravitational force is uniform, when the moment is near the Earth's surface, but not, it is not the actual picture. What is the actual picture? Let us see. Consider a particle, moment of which is confined in a region of linear dimensions much smaller than the radius of the Earth. The gravitational force on the particle due to Earth as well as acceleration due to gravity, G vector, can be assumed fairly uniform. What I am saying? Not limited near to the Earth. The particle may be anywhere, but its movement is confined in a region. The linear dimension of that is much smaller than the radius of the Earth. So in that region, wherever it may be located, gravitational force from the Earth can be assumed fairly constant or fairly uniform, as well as gravitational acceleration Z vector. So it is not that this for to assuming gravity uniform, the moment must be near to the surface. What? The region of movement must be much smaller than the radius of the Earth. But what is the idea? For terrestrial bodies, means the body is moving near the Earth's surface, say even maybe aeroplane. So height of the aeroplane from the Earth means the movement of the aeroplane in a region which is much smaller than the radius of the Earth. So for all terrestrial bodies, we can assume gravitational force to be uniform or acceleration due to gravity to be uniform. This condition is fulfilled by motion of all the terrestrial objects. That's why in lower classes, these potentials were defined for moving a stone or moving a ball from a height h1 to h2 near the surface. So at that time, we can see gravity is uniform. But gravity may be uniform in other cases also. And that case is defined here. Thus, for simplicity, we consider a ball of mass m that is shifted from a height h initial to h final near the ground. This ball is a terrestrial object, and we try to develop expression for potential energy of Earth ball system. In what condition? The ball is lifted from a height h initial to h final near the Earth, and this difference h is much smaller than the radius of the Earth. See here the figure. This ball was initially at height hi. Now it is shifted to height hf, and this h is much smaller than the radius of the Earth. So throughout this moment, gravity can be assumed uniform. And here is the preview diagram. That is mg, weight of the ball, and here the applied force which is used to lift the ball. And here you can see very carefully this F factor I have shown somewhat greater than mg. Of course, to lift the ball, the F must be either slightly greater, but I have shown here considerably greater. Now the ball will have accelerated motion. Of course, work done by this accelerated agency will be utilized in two ways. Increasing potential energy of the Earth ball system means doing work against gravity and supplying kinetic energy to the ball. But if we forget about this force, we consider only gravity, that is conservative force. Work done by gravity will be minus mgh, And what is saying? Negative of work done of the conservative force is equal to increase in potential energy. So we can say minus mgh, negative of that mgh will be equal to increase in potential energy U final minus U initial. Oh, that is what basic formula. Let us again execute this mathematically. Here we assume a small displacement dh, upward direction. So what is definition of potential energy? Du is equal to minus F vector internal conservative dot dr, means negative of work done by conservative force internal is equal to increase in potential energy. So for mg internal conservative vector, what we put mg vector, and for dr vector, what we substitute dh vector. So this will be du is equal to minus mg vector dot dh vector. Now you can see mg vector and dh vector are opposite. So this dot product will be minus mg dh, and that minus sign and this minus sign will become positive. So what will du? mgh, mg dh. Now we perform integration. What definite integral u initial to u final is equal into du, that is from hi to hf mg dh. So this left hand side we get u final minus u initial, and here we get mg hf minus mg hi. Now we can simplify it mgh. So what we get? U final minus U initial equal to mgh. Here again we have liberty to assign a reference, and usually this reference is not, I'm not saying that is this reference should be ground. Say hi we are choosing as a reference. So if we assume hi to be reference, so potential energy here ui will be 0, and this is what mg common hf minus hi, that is mgh. So we assume its value to 0. So uf we say u. So what we have here, u minus 0 is equal to mgh. So u is equal to mgh. In that way we have seen the potential energy of this earth ball system. And what is that? H is not height of the ball, it is what? Change in height. So you can see it is change in potential energy. That's why we are saying the potential is fundamentally defined as a change. So this is the expression for gravitational potential energy for a uniform gravitational field. So that relation you know very well, but what we have to understand here, that is this idea. When gravity can be assumed uniform, means gravity of the earth. This is the potential energy of the earth ball system. Now after we have developed expression for potential energy in uniform gravitational force, now let's proceed how we obtain expression for potential energy in non-uniform gravitational field. But again on the same line, as I'm saying, for uniform gravity the location of the bodies must not be limited only near the surface. They may be anywhere, but their movement must be limited in a region whose size is much smaller than the radius of the earth. Similarly, for non-uniform gravity, the idea is very simple. It is not that bodies must be far away from the earth. Actually, movement of the body must be in such a region whose size, whose linear dimensions must be comparable or much larger than the radius of the earth. So let us proceed how to develop gravitational potential energy for a non-uniform gravitational force. Gravitational potential energy for a non-uniform gravitational force. If movement of a particle is in a region, linear dimensions of which are comparable or larger than the radius of the earth, the gravitational force on the particle due to earth cannot be assumed uniform. So that is what we mean by non-uniform gravity. Say, to assume gravity to be non-uniform, only saying that the particle must be far away from the earth is insufficient condition. What is sufficient condition? Wherever the particle is, its movement must be in such a region whose linear dimensions must be much larger than the radius of the earth or comparable to the earth. Consider a ball that is shifted radially from a distance r1, ri, from the center of the earth to a distance r final. See here in the diagram, the ball was shifted from this location ri, r initial, to this rf means r final. this ball has to be shifted from here to here. Now you can see the region of this moment is larger than the Earth radius. So in this, for this, gravity cannot be uniform. Suppose this ball was shifted from Ri to Ri plus 100 meter. So for that 100 meter, the gravity here can be assumed uniform. But here this moment size is much larger, or comparable or larger than the radius of the Earth. So gravity cannot be assumed here uniform. Now he can see this is a dr vector, infinitely small displacement, and this is Fg, means gravitational force, and that is applied force which is used to shift the ball here. Again, not necessary that this applied force must be equal to gravity. It may be greater. If it is greater, then what we obtain? Work done by this action agency will be utilized partly work done against gravity and partly increasing current of the ball. But if the F is equal to Fg, the ball will move without acceleration. In that case, the work done by this force will be completely utilized in doing work against gravity. So du is equal to minus F internal conservative dot dr. That is definition of potential energy. Now for this what we take? Fg vector. For this we have dr vector. So du is equal to minus Fg vector dot dr. And Fg vector, say in this direction, dr vector in this direction, again the angle is 180. So this dot product will be negative. So that negative and this negative will become positive. So what you get here? Fg into dr. So we substitute value of Fg, gmm by r square into dr. So du is simply gmm by r square dr. Now to find potential energy change from this configuration to this configuration, we perform different integral. For this configuration, say ui, initial. For this configuration, so say u final, uf. And so this integral will have limit ui to u final, and this integral will have limit ri to r final. So ui to u final, integral du is equal to gmm, we can take outside, dr by r square from ri to rf. Now this integration is not difficult. What you can write here? U final minus U initial is equal to gmm by ri minus gmm by rf. Again in this situation, we can define a point as a reference. Now we have two choices. Either we can define reference here on the Earth surface to 0, or we can say reference infinitely away from the Earth to 0. Which we should choose? Actually, in the spring case, it was very obvious. When the spring is relaxed, say that is reference. But in this case, we have two choices, either here or there. Which one we should choose? Naturally, you will say, yes, we have to choose reference here. But what will happen here? If we choose reference here, means we can say this value of r and this value 0. So u is what? This minus rf. So as rf is increasing, what we can say? As rf is increasing, this value will decrease. And at infinitely away point, this value will be what? Gm by r. So as we are moving away, the gravitational potential is decreasing, and very far away from the Earth, the value, this right hand side will become infinitely small. Now see what will happen with the space missions. Actually, this relation we will use for space mission. We will to study what is happening in space, satellite, planets, or we are sending some space mission like a Mars mission. For that we use this formula. And far away from the Earth, this left hand side will look infinitely small. So their change between two values will be infinitely small. It will be very difficult to calculate. But what will happen if we choose reference at RF when infinity to 0? Then we have some other things. As we are moving away, potential energy change will increasing. So far away point we have larger value. So at that point calculations will be somewhat simpler. So here what we choose? We choose reference configuration when separation of this ball is infinitely away from the Earth. That at that place we assume potential to be 0. One more thing, if you take RF to be reference, RF infinity, so this value will be 0 and this value will be 0. So again here you can see very simple mathematics. Assuming the reference configuration RF tends to infinity, we make substitutions UF equal to 0, RI is equal to R, and UI is equal to UR, means your potential Z at separation R. And RF tends to infinity, we are choosing a reference and assigning it to value 0. So what we took here, we take here 0. This will ultimately tend to 0. It will be again 0 because here infinite. So what we have, minus U I instead what you get UR. Minus UR is equal to GM by R. So what we have, U at R is equal to minus GM by R. So 0 minus UR is GM by R minus 0. So what you get here, U at R is equal to minus GM by R. So this is the expression for potential energy for a configuration. What? The separation between the earth and the body is R. And of course here, where is the reference point? When the body is infinitely away, it will have no potential energy. One more idea is there. At infinitely away points, to move the body from, actually in far away in space, we have no gravitation, of course negligible gravitational force. So at that time, to move the body anywhere against gravity, we require very little effort. And again we say with this formula, when R is very large, this value will be very small, so difference in potentials will be very small. So we can say neglect that change. So we can say far away from the earth, the body is almost free from gravitational influence of the earth. So what we can see here, this is the expression for the gravitational potential energy, assuming reference configuration with the infinite separation between the ball and the earth. So that is what this expression will be used when we cannot assume gravity to be uniform. So that was two formula. Now we can proceed further with the examples. Say example 1. Now what the idea we have developed, we try to apply these ideas in few questions. Say what is the first question, let us see. Find gravitational potential energy of a rod earth system where a thin rod of mass m and length capital L is held at an angle theta with one of its ends on the ground. Assume the ground as the reference potential energy level. It means when some particle is at the ground, its potential we assume 0. So that was situation given here. This rod is held at angle theta, which one end touching the ground, means lower end is touching the ground. Now we have to find gravitational potential energy of this rod earth system. Actually, in very crude language, say gravitational potential of the rod, but what is true sense? Gravitational potential energy of the rod earth system. So what is the idea? This rod is not a particle, this is the extended body, so we can assume large number of particles. So every particle of the rod is interacting with the earth through its gravity. So what idea is, we calculate gravitational potentials of each pair and add them, and number of pairs are infinite, so we have to use integration. So instead of a particle, we assume a small portion, infinitely small portion that can be treated as a particle. So we calculate potentiality of that pair and add potentiality of all possible pairs, as we have seen what is meant by potentiality of a system of many particles. Consider an infinitely small portion of length dl of the rod at a distance L from the lower end, as shown in the figure here. Say that is rod. We are again reproducing the figure. Now from this end at a distance L, we assume a infinitely small portion of the length dl. This portion of the length dl. Of course, this portion has shown a finite length, but we have to assume mathematically it is infinitely small, just like a particle. And we can see height of this portion is, say, h. So h is equal to L sin theta. Very easy. This length is L, so this is what? L sin theta. Denoting mass of this portion by dm, the gravitational potential energy du of this portion can be expressed as, if saying du of this portion, what does it mean? Du of this portion and earth system. So that will be again, we assume a ball at height h, and here it was potential energy was on 0. So if this particle was lifted from here to here, the change in potential energy is what? dmgh. So du will be what? dmgh. So we can write here dmgh. Now this is what? Potential energy of interaction between this particle and Earth. Now we search all such particles and write their potential energy in it. So here, before we proceed for dm, what you can write here? M by L, mass per length into dl, that is dmgh. So m by L gl sine theta dl. We can substitute for h. H is what? L sine theta. So what you get here? M by L gl sine theta dl. As the rod consists of infinitely large number of such segments, to find the total potential energy of the rod earth system, we have to sum potential energies of all the pairs made by each segment with the earth. Actually, this is the idea we have discussed earlier, and how that is the idea how we can calculate potential energy of a many particle system. Now for this purpose we have to make a different integral. What is that? The gravitational potential energy U of the rod, limit 0 to U in du integral from L is equal to 0 to capital L m by L gl sine theta dl. What does it mean? When L is 0, the segment, infinitely small segment is here, so at the ground, so its potential energy is 0. Means potential energy of that segment or system is 0. As we move further, potential energy is increasing, and if when we are counting the last statement, the sum has become U. So that is limit 0 to U, and limit here L small l equal to 0 to L. Now this is very simple to calculate. So what you get here? M by L g sine theta, and L equal to 0 to L, because this constant term we are taking outside. So this integral will be U minus 0 or U. So mg L by 2 sine theta. Very simple to calculate, because this is what? L square by 2. So this L will cancel, so we'll get simply L by 2. So what I write here? mg L by 2 sine theta. It has another interpretation. What is L by 2? L by 2 is, if the rod is uniform, that is its mass center. So L by 2 sine theta is height of the mass center. So can we do one thing? To calculate potential energy of a mass distribution, we can assume the entire mass distribution as a particle on its mass center. Let us see further, can we do it? If we are finding such kind of thing in several problems, at present we make as a shortcut to find potential energy of a mass distribution, but we again verify this idea when we study about mass center. Let us come on the next example. Example 2. Find the gravitational potential energy of a rope or system where a uniform rope of mass m and length L is held on a frictionless hemispherical dome or hemisphere of radius capital R as shown. Assume the ground as the reference potential energy level again. So this, on this frictionless spherical dome, this rope is held. The top point, one end of the rope is at the top point of the hemispherical dome. Now we do the same thing. That is, rope is a many particle system, so we assume a particle means infinitely small part, and we calculate potential energy of that infinitely small part and the earth system, and then sum up all pairs, sum up potential energy of all such pairs. So what we proceed here, consider an infinitely small portion of the length dl of the rope at a distance L from the top end. So here in this diagram, we assume this dl from this end at distance L, this small portion is dl, and we can define its position coordinate by this angle theta this way, and its length by angular span d theta. So this end is at angle theta, this end is at angle theta plus d theta. So angular span for this is d theta. Now we can see here, this angle theta is measured to be 0 here, and what is angle theta here? This arc length upon radius is r, so this is theta is L by r. So theta value changes from 0 to L by r. Now to write potential energy of this part and the earth system, we have to locate its height. So its height is this r, this theta. So height is r is h is equal to r cos theta. Now we are having enough information to proceed further. Again we assume dm, denote mass of this portion dm. So dm we can write m by capital L into dl. So denoting mass of this portion by dm, the gravitational potential energy du of this portion is, so du is equal to dmgh. So gh, h is this. So substitute value of dm is what? M by capital L into dl. M by capital L into dl, and g and h is r cos theta. Again for dl we can substitute r d theta, this arc length. So what we proceed? M by L r d theta, g r cos theta. Now from if you see from portion to portion to portion, only theta is variable from all these symbols. So d theta we write here. So what we are getting here? mg r square by L cos theta d theta. So d is equal to m by L gr square cos theta d theta. Now we sum this du for all possible infinitely small pair in Earth. So we have to perform different integral. The gravitational potential energy u of the rope, that is from 0 to u du is equal to from theta equal to 0 to L by r, this expression m by L gr square cos theta theta. So m by L gr square we can take outside because that is a constant. So what we are getting? M by L gr square integral 0 to L by r cos theta d theta. And this integration is very simple. I am writing here the results straightforwardly. U is equal to m by L gr square sine theta L by r. Again just see the idea what we have done earlier, that is to write potential energy of a mass distribution, we can assume the entire mass distribution at its mass center. In so many situations we can find where is the mass center, but for this arc-like rod rope we cannot say where is the mass center. So here we have to proceed with this method. But when we study about mass center, we'll have some formula to find mass center of an arc. We'll see later when we study mass center about that. So let us come on the next example, example 3. What is that? Find the gravitational potential energy of a liquid filled up to a height h in a cylindrical vessel of radius small r. Mass of the liquid is m. So in that way, radius of this vessel is r, so diameter is 2r, and liquid is filled up to height h. Of course, see, if it is liquid, it means we will say liquid of uniform density. So what we again do, we can assume liquid to be made of infinitely small part, but here we can have some simplicity. Instead of making infinitely small particle, we can say infinitely thin layer, because every portion of this layer will be at equal height. So suppose we take a dm, this layer made of large number of dm. So for every dm, energy is what? dmgh. So for all we 8, so mass of this layer into gh will be potential energy of that layer. And now we perform integration from as this 0 to h. So let's proceed here. Consider an infinitely thin layer of thickness dy of the liquid at a height y above the ground, as shown in the figure this way. So here we assume infinitely thin layer at height y and thickness of this dy. We assume mass of this layer denoted by dm, so we can write dm. Dm is what? Area of this cross section pi r square into height dy, so volume into rho, that is mass, and g into y will be potential energy of this layer. Let's write it how we can obtain. Denoting mass of this layer by dm, the gravitational potential energy du of this layer is du is equal to dm gy. And what is dm? Rho pi r square dy gy. And again here in this you can see only y is variable, so we can write here rho pi r square g y dy. Rho pi r square g y dy. Now we perform integration from y is equal to 0 to h and u is equal to 0 to u. The gravitational potential energy U of the whole liquid, that is 0 to U du, y equal to 0 to h, rho pi r square g y dy. So rho pi r square g we can take outside. So rho pi r square g into y to h y dy. So this integral will be y square by 2, basically h square by 2. So what we get? U is equal to rho pi r square g h square by 2. Now we can write one thing. Rho pi r square h into g h by 2. Now you can see rho pi r square h is the volume, rho multiplied into volume mass. So m, this is mass, g h by 2. H by 2 is the height of mass center. So again you can see this idea is valid. Of course, in the case of arc shaped rod, the idea was valid, but at this juncture of time, we have no idea how to calculate mass center of that arc rod. But when we calculate the mass center, the idea is valid. So here we can make a conclusion. What? To find gravitational potential energy of a mass distribution, we can represent or we can replace the entire distribution by a particle of the same mass at the mass center of the distribution. So U is equal to mgh by 2. M is mass of the liquid. So for this we replace M. Now we are the idea we have made here regarding mass center and gravitational potential energy, I am writing here as a note. Gravitational potential energy of a continuous mass distribution can easily be calculated by assuming entire mass as a particle at the location of the mass center of the distribution. So this idea, wherever we'll find the location of mass center, we know that for a uniform mass, location is the mass center is at the centroid of the distribution. But centroid of distribution in every case we cannot find. But in which case we can find the centroid of distribution, we'll use that idea to find gravitational potential energy. So let us come on the next example, example 4. The system shown is held motionless. Masses of the blocks A and B are 4m and m respectively. The thread and the pulleys are ideal. Find change in gravitational potential energy of the system if block A descends a height h. So this system is given. The block A has mass 4m and B has mass m. We have to find change in gravitational potential energy when this A descends height h. Now again, this is what? System of particle, means 3 particles or 2 particles A and B and Earth. So we have many particle system. So again, what we do? The simple idea to find the change in total gravitational potential energy, we consider each pair A and Earth and B and Earth. Find change in gravitational potential energy of these 2 pairs and add them, and that is a simple idea. So how we proceed? Constant relation before to find change. Of course, movement of A is given h. So how much B will move? That we have to find constant relation, and that is very easy. That is visual inspection. So when A will descend height h, B will rise to height 2h. How? When A will lower by h, so here h length of rope will increase and h length here will increase. So from between these two points, total increment of the rope length is 2h, so it will be supplied from here. So B will rise to a height 2h. When the block A descends a height h, the block B rises to a height 2h. That is simple idea. Now we proceed here. This initial configuration of the system and final configuration. We have assumed A has been lowered by amount h. So B will rise to a height 2h. So this is 2h. So this constant we have seen. So now how we'll proceed? We calculate change in gravitational potential energy of each pair, A and Earth and B and Earth, and add them. Gravitational potential energy of the system is due to gravitational interaction of the blocks with the Earth. So thus, change in gravitational potential energy of the system is equal to sum of changes in gravitational potential energies of each block Earth system. So let us proceed with this idea. So delta U will be delta UAE plus UB. What is UAE? Potential energy of A Earth system and B Earth system. So delta U will be delta UA plus delta UB. And delta UA is very simple to write what? And that is 4 mg with minus h. So minus 4 mgh, and this will be mg into 2h. So it will be 2 mgh. So what we get here? Minus 4 mgh plus 2 mgh minus 2 mgh. So this is minus 4 mg into gh, that is mg into 2h. So what we get? Delta U is equal to minus 2 mgh. So that is total change in gravitational potential energy. Now we proceed with the next example. Example 5. Find potential energy function associated with the force. What the force is? F vector is equal to K by R cap. R cap is the unit vector along R away from the origin. So that is a force, and such kind of force whose magnitude depends length of position vector and direction is along the position vector, either towards origin or away from the origin, are known as central force. And we discuss about central force when we talk about conservative forces. Here K is a positive constant. So how we proceed? That is the interaction force. So simply work done by interaction force conservative will be equal to decrease in potential energy, or increase in potential energy is negative of work done of internal conservative force. So everywhere the force acts towards the origin. Let us think about the force. Because we have minus sign, it means force is towards origin this way. If we place a particle here, the force direction will be in this direction. So F will be here, this F vector, because of this minus sign. So we assume a dr here. So this dr, so du will be what? F dr minus sign. So from the definition of the potential energy increment, we have du is equal to minus F internal conservative dot dr. Now for this, what is substitute? F vector for this dr. So F vector dot dr. So F vector and dr have angle 180 degree. So this dot product will again F into dr with minus sign. So minus minus will become positive. So what you get here? Minus F dot dr. So this is basically F into dr. So we substitute value of F. So minus K by R vector this. So minus minus will become plus. So R cap dot dr will be again R. So K dr by R. Now we have to perform the definite integral. But what will be limit? Here we can say limit Ri to Rf. But what will be limit here? Here we cannot say 0 to U. Again here we have to take from U initial to U final, because earlier in all the problems we are taking 0 to U because it was given that ground is the reference potential level, 0 level. But here no such a reference is specified. So we have to select our reference. So the definite integral limit will be what? From U initial to U final du is equal to R initial to R final K dr by R. So we can take outside. So dr by R ln R. So that is K Ri to Rf and dr. So now what we get here? This will be U final minus U initial K ln R final minus K ln R initial. So this is what idea we have. So U final minus U initial is K ln R final minus K ln R initial. Now this is the expression. Here we have to assign a value 0. Of course, in principle we can assign any value 0. But to which? Of course, if a 0 and 0 correspond from this side to that side, it only when we have simplicity. So here when R is equal to 1, only when a term will be 0. Again, taking R1 is equal to 0 and assuming when R1 is equal to R is equal to 1 and U is equal to 0 is again a very particular reference. It will make no sense. It will not introduce any simplicity. So what is advised here? Here it is advised not to define any reference, only use this formula, because ultimately we are always interested in the value of change in potential energy, and this formula will directly give the change in potential energy. So what we can conclude? Here we can assign a value 0 to the potential energy function only at Ri is equal to 1 meter, but it will make potential energy at Rf to infinity. thus will make no sense. Again, here I talk about a mathematical term. So here defining a reference is make no simplicity. So it is not necessary that in potential energy function we are always in a position to assign a configuration zero value or a reference configuration. So whenever it is choosing a reference will not make the expression simpler. So what is advised? To leave the expression as it is, because ultimately we are interested in the change in potential energy. Since it is a change in value of potential energy that has significance and not the absolute value, we can use the above relation as it is. So that is what recommended. Conclusion regarding choosing the reference. When we can choose the reference and we cannot choose a particular reference. When choosing a reference will make the expression simpler, we choose the reference. When choosing a reference will not make the expression simpler, we use such kind of change relation as it is. So let us summarize this as a note. What? It is not always possible to assign a value 0 to the potential energy to a configuration. Means only when to a configuration we can assign a value 0, it will make simplification. If we had to assign a configuration particular value, then it will not make the relation simpler. In that case, whatever relation we are finding, the same relation will use to calculate change in potential energy. In such situation, still the expression obtained will yield the change in potential energy between two configuration, and that is what in which we are interested. Now we proceed with the conclusion regarding home assignment. So what is home assignment? As usual, you have to revise all the ideas and examples covered today. Revise all the ideas and examples discussed today in this lecture. Again, you will find a module of work energy power on the group today, and from that module you have to attempt some questions, because how much we have covered in this chapter, now it is proper time to have proper practice of that. Attempt question number 1 to 63 of exercise 01 in the module, and this module you will find today in the group. Thanks for patient listening. We'll meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.